I want to talk a bit about the logic of exponents. That is, what's the basic concept? What do they mean? As always, our motto in this class is use your normal brain, and an exponent is simply a thing you can understand, and when you understand what it is, you can see how it works. I'm trying to fight the common habit of memorizing techniques for solving problems. That seems to be what math class is for. How it works, the professor tells you what to do in a particular situation, and you hope to pound the steps into your brain so that you remember them on the test, after which, of course, you forget them. That's not a good way to proceed. But if you understand what exponents are, then you can find the techniques you need to solve the problems that come up. And these problems will, at least we hope, come to you when you have the kind of career we hope you get, dealing with large numbers, dealing with populations of people, dealing with large budgets. Both money and people grow, and to solve those problems of how fast things grow, you really need to have some facility with exponents, and also their inverse, the logarithm. That's our further goal. Can we understand logarithms? They're sort of spooky and scary things, abstract concepts that people who don't like mathematics very much have trouble with, but we're going to see if we can understand them. We saw a little of that in this graph that we looked at for last Thursday's class. You will remember this graph, which gives us information about the spread of diseases and epidemics. And if you look at the graph, you see there seems to be something funky on the y-axis at the left margin. It's not an even scale. Different amounts of distance, different spaces seem to mean different things depending on how high up the page they are. There seems to be something regular and useful about this graph, and that's certainly true. But there's something odd about it as well. So let's see what we can figure out. Just blow up the part that we're interested in. If we look, it seems like this part down here a little chunk of space represents a small number. That seems to be the difference between 0.1 and 0.2, 1/10 of 1%. Up here we see that what looks like the same amount of space, and indeed it is the difference between 10 and 20, 10%. That doesn't quite seem to make sense. Of course, if we recognize that it's identified as a log scale, we can begin to get a clue that in fact it does make sense. But this is the sort of problem, a problem of growth, that we're headed toward, and the sort of mathematical tool we're hoping to understand. Now, just to look back, earlier last week I asked you a question. I asked you what 10 to the power of 1/2 was, and my goal was not to get that precise answer, but to see who could understand what a fractional exponent was. And indeed, some people do understand. That seems to be the right answer. Anything raised to the 1/2 power is a thing taken to its square root. I got the right answer in different forms. That number with its decimal is at least an approximation of what that means. Not all the answers were correct, and some of them were honest and helpful. Now, on a second go around with a little explanation, people remembered what they already knew, people understood better, so that's progress. But let's see if we can expand on the concept so that people really do understand, and that will support the development of the ideas we're working with. Now, I'd like not to jump right in with fractional exponents and talk about what they mean, but to start closer to the first puzzle, Exponents are not hard to understand. We know that 10 to the third is 10 times 10 times 10. That's easy. But the first thing that seems conceptually difficult is, what is 10 to the 0 power? Well, you probably do remember the right answer. That's 1. But the question is, why is that the right answer? You might not have a ready answer for that, but that's the kind of thing that you need to know to understand this branch of mathematics and be prepared to use it and move forward. One answer is that 10 to the 0 power is 1 because any number to the 0 power is 1. So 3 to the 0 power, a small decimal, a big number, they all come out to 1. So that's the way you do it. Now, that's my least favorite answer. That doesn't really help anyone. It just says that it's true because that's the way we do it. That should be unsatisfying to you. And maybe the first step to understanding is to recognize that it feels wrong. You're taking something to the 0 power, and 0 means nothing, and nothing should lead to nothing. But it seems that in exponent world that we use nothing to create something. Well, it seems backwards for mathematics. If we had 10 to the third power, we'd have 3 tens all multiplied by each other. Well, what if we had no tens at all? Well, it seems more natural to say, well, then we'd have 0. But the answer somehow is that we've got 1. So can we make sense of that? It seems that 0 ought to be the neutral starting point, and the neutral starting point to anything in mathematics seems to be 0, just as when you turn your calculator on, it shows you a 0 as a sign that it's ready to begin. Now, so to begin on an answer, why is this true? Why is 10 to the 0 power anything to the 0 power? Why does it equal 1? We could say, well, it fits the overall pattern of everything else we do with exponents, and that's at least a halfway step to understanding. The whole use of the rules are consistent. Things match each other when we do it that way. So let me see if I can show the pattern to say what I mean. If we have 10 to the third power, we know what that means. As I said a minute ago, 10 times 10 times 10, that's 1,000. If we only have 10 to the second power, that should be the same as the first number divided by 10. So 10 to the second power is 2 tens multiplied by each other, and that gives us 100. 10 to the first power is a little bit funky, but it's not hard to understand, and it doesn't feel wrong to say, well, you've got exponent, you've got just 1 10. And so we see the pattern emerge that each line as we go up is the value of the one below it with an extra 0 added or multiplied by 10. If we go from the top down, every time we get a new line, since we're subtracting 1 for the exponent, we're dividing the number by 10. And this is consistent. But now we get to 10 to the 0, and it still feels a little off that we should just put in the number 1 when we don't have any tens at all. But we can go to the further step. If we get into negative exponents, we know what those are. And those don't feel wrong to us. That we have 1 divided by 10, so 10 to the negative 1 just moves the decimal point over. We get 0.1 or 1/10. And that should give us a clue as to what has to come in the middle. We should divide the basic number by 10 to get 10 to the negative 1 power. We should divide 10 to the 0 by 10 in order to get 10 to the negative 1. But if the number we were dividing by 10 was 0, then the result would be 0, and every negative power would have to be 0, because if you've got a fraction with 0 in the numerator, 0 on top, doesn't matter what you've got in the denominator, you're always going to end up with 0. So that might start to make the authoritative answer, the recognized answer, the conventional answer, feel like the truth to you. We can continue the pattern. As we will go down, we subtract another single-digit exponent. We subtract another unit from our exponent. We go down from -1 to -2. Then we've just divided the number above by 10. And the whole pattern seems consistent. Every time we go up a line, we multiply by 10. Every time we go down a line, we divide by 10. And there's only the question of what goes in that gap in the middle that we don't quite feel right about. Well, it's going to have to be the number 1. That's the only thing that saves the consistent power. If we put a 0 in there, then the whole pattern would be interrupted right in the center. I can say similar things another way by looking at an actual calculator, as I said before, and the calculator gives us the notion that 0 is the starting point, and it makes it make intuitive sense to give the wrong answer, that if you have 10 to the 0 power, you have no 10s at all, and you should start in the basic starting place with nothing, and that the mathematical way to express nothing is with the number 0. And while it's certainly true that the mathematics express nothing with the number 0, there's a hidden assumption here that when I start my calculator, it shows me 0 as a sign that I'm ready to begin, and then I can punch in whatever number I want to work with. But the hidden assumption is that when I tap something in, what my calculator is going to do is add that new thing to whatever it's got already, and that's why I need a 0 to start with, because when it comes to adding, 0 is indeed the neutral number that lets me get started. So if I take what I have already and I add in 55, then I get what I wanted to think about the number of 55. Now, if my calculator were to assume that the basic operation is multiplying, and of course with exponents, the fundamental operation at the bottom is multiplying. That's why 10 squared is 10 times 10. If my calculator assumed that I wanted to multiply, if I typed in a new number, I wanted to multiply it by whatever was there, then 0 would not be the neutral number, and would in fact make my calculator useless, because whatever I did with it, it would always just return the answer 0, and I could never get going on anything else. If my calculator thought of itself as living in multiplication world rather than addition world, which is proper for exponents, since that's what exponents are, then the neutral number would indeed be 1, so that anything I typed in would be available for me to work. Maybe give a better answer to why any number raised to the 0 power is 1. It's because 1 is the neutral beginning number for multiplication, and that's the essence of an exponent. Any exponent is a base x multiplied by itself y times or divided. We can remember the complication, so that for any exponent, what do? Well, before I fix the base or the power, I start with 1, because that's the neutral number. If I have 10 raised to the second power, I have 1 multiplied by 10 multiplied by 10. If I have 10 to the -2 power, then I start with 1, as I always do, and negative multiplier divided by 10, negative multiplied divided by 10 again, and I get 0.01. And so what is the number raised to the power 0? Well, that's neutral, as we know it must be, so it's the neutral number not multiplied or divided by any